Hi everyone. In this video, I will tell you about mesh analysis. Mesh analysis is basically a method which is used to determine mesh currents, and subsequently you can also find branch currents. Before understanding what a mesh is, we should know what is a loop. A loop is simply a closed path traversed by a current. For example, this is a loop, this is also a loop, and this is also a loop. If you see this loop, this is you can say a little bit special in some sense, because in this loop no subloops are possible, and hence this is a mesh. So a mesh is such a loop which does not have any subloops. So in this circuit, this is a mesh, this is also a mesh, and this is also a mesh. So let's assign mesh currents. As you can see here, I have chosen clockwise direction of current in all the three meshes, and this is necessary because you can't do this like this is clockwise and this is anti-clockwise. You have to either choose anti-clockwise in all the three meshes or clockwise in all the three meshes. After identifying meshes and assigning mesh currents, the next important step is writing Z matrix, and this is like Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33. Now let's understand the meaning of elements. Z11 is the impedance of mesh 1, Z22 is the impedance of mesh 2, and Z33 is the impedance of mesh 3. And Z12 is the negative of the impedance common between mesh 1 and mesh 2. That is, it is negative of common impedance between mesh 1 and mesh 2. And clearly, this will be equal to Z21. Similarly, you can define Z13, that is minus of common impedance between mesh 1 and mesh 3, and Z23 as negative of impedance common between mesh 2 and mesh 3. And these elements like Z21 will be equal to Z12, Z31 will be equal to Z13, Z32 will be equal to Z23. So this will be a symmetric matrix. Now we can use equation matrix Z multiplied by matrix I equal to matrix V, and this is simply KVL. This matrix V is voltage source matrix. To illustrate this, let's solve this circuit. For this circuit, Z is first element Z11, that is impedance of mesh 1, 5 plus 1. So first element will be 6. Z12, impedance common between is 1, and we have to write with negative sign. So this will be minus 1. Z13, impedance common between mesh 1 and mesh 3, and this is 0. This will be equal to this. Z22, with the impedance of mesh 2, this will be equal to 1 plus 3 plus 7 equal to 11. Z23, minus of impedance common between mesh 2 and mesh 3, this will be minus 7, and this will be equal to 0, and this will be equal to minus 7, and Z33 is the impedance of mesh 3, this will be equal to 9. This will be I1, I2, and I3 equal to V matrix. In mesh 1, the voltage source is plus 10 volt, plus 10. In mesh 2, there is no voltage source, so this will be 0. In mesh 3, this will be equal to minus 5. The reason I have written minus 5 is the convention we have chosen is from low to high, it is taken as positive. So I1 is going from low potential to high potential, so this is plus 10. But in this case, I3 is moving from high potential to low potential, so this will be negative. And from this you can get three equations, and there are three variables, so solving them you can get these values of I1, I2 and I3. In this case it comes out to be 155 by 97. I2 comes out to be minus 40 by 97, and I3 comes out to be minus 55 by 97. This minus sign indicates that the actual current will be in the direction opposite to the direction we have chosen, and similarly I3 will be in the opposite direction we have chosen. And now, as you know the mesh currents, you can easily find the branch currents. In this branch the current will be I1. In this branch current will be I1 minus I2, because I2 is in this direction, sorry, I1 is in this direction and I2 is in this direction. In this branch current will be I2 minus I3, because I2 is direction and I3 is in direction, so I3 will be subtracted and this is I3. If you think that this will be very time consuming to solve these equations, then you can use calculator, and using that you can find it very easily within literally no time. So that's all about mesh analysis. Thank you.